Now let's talk about the section 6.8. Exponential growth and the decay models. Newton's law. Logistic growth and the decay models. Okay, so let's see one process. Assume you have one cell in the human being or in the animal growing process. One cell, after some constant time, the cell will divide into two identical cells after a certain constant time. Let's just simplify it. Just assume this one cell divides into two cells in constant time. This is time, a constant time. And after next constant time, each cell divides into two new cells, and then after another constant time, each cell divides into two new cells. So this process will continue, and you will see that the number of the cells, see here, this is 1, this is 2, this is 4, this becomes 8. And if you write it in a certain pattern, it is an exponential function. It's an exponential function. An exponential function with base 2, this power is a number of is a time. The exponent is represented by the time. And in the exponential function, remember that no. For arbitrary number a, it is equal to e natural log of a. Remember this. This is what do we say? This is the identity. You cancel the exponential with the natural logarithmic function, you get a for positive a. And let's apply this property for this. So we will see that 2 to certain power. So this one, it follows the property 2 to t. So 2 to certain power, 2 to t, assume it is a, so it's a e natural log 2 to t. And this is a power, you move power forward. It's natural log of 2 times t. We like this exponential function instead of this exponential, because of this one we choose a fixed base. Here you have 2 because you are talking about this problem. You talk about this problem, you have 2. Maybe there's another type of cell. After each constant time, one cell divides into 3 new cells. So you have to change the base from 2 to be 3. And maybe you have another property, it is divided into 5, so you have to divide each cell divides into 5 new cells. You have to change the base to be 5. So you always change a base. That's not what we want. So we want this base, constant base, a fixed base. So we'll assume the base is e, and this number, it depends on the problem. For different problem, we choose a different coefficient. The coefficient depends on the problem. Okay, so this is going to be the function we study, and this is why exponential function is very important. Okay, so to make this problem, or to make this discussion more theoretical, we define the following function. A function a of t, it is defined to be a0 times e to kt. a0 times e to kt. This is a target function we are going to study, and it's called let me say the name. It's called the an amount a varies over time according to the above equation. It is said to follow the exponential law or the law of uninhibited growth. If we use this word growth when this k is greater than 0, or we use decay when this k is less than 0. Okay, so it is said to follow the exponential law or the law of the uninhibited growth with k positive, or law of uninhibited decay when k is negative. We use different word. Growth or decay is because when k is positive, a0 is always positive. Here, a0 is always positive. When k is positive, the graph of functions like this. When k is negative, the graph of functions like this. So this is an increasing function, this is a decreasing function. So we call this situation a growth, we call this situation a decay. Okay, so we start from a simple division process. Each cell divides into 2 after a certain amount of time. And then you will observe that the number of the cells after several processes is an exponential function with a base 2. And sometimes we prefer this new base, e. So we use this property to write 2 to t as e to kt. K is, in this problem, k is a natural log of 2. So we like this e to kt. And you see that this is a growth process. Okay, so this e to kt possibly controls the whole process. That's why we are interested in this type of equation. A of t is equal to a sub 0 times e to kt, and this may covers or this may controls many similar process, and this process is called to follow exponential law or the law of uninhibited growth or decay. Okay. In the uninhibited growth of cells, and we pick up the growth case, and let's study this growth case. Okay, so a model that gives the number n of cells in a culture after a time t has passed is n of t equal to n sub 0 e to kt, and because this is growth, so k is positive, where n sub 0 is the initial number of cells, and k is a positive constant that represents the growth rate of the cell. Okay, so this is a uninhibited growth of cells. Uninhibited growth of cells is just this process, and it's one of the cases from the law, exponential law. Okay, so we have this formula. Keep this formula in mind. Let's do examples. After examples, you may understand it better. Examples. So let's talk about the story. A colony of bacteria that grows according to the law of uninhibited growth. Is modeled by the function n of t is equal to 100 exponential e to 0.045 t, where n is measured in gram and t T is measured in days. Okay, so here we do not count the number of the bacteria. It's difficult. So we measure the bacteria in gram, the weight. Okay, so let's understand this expression. First, determine the initial amount of bacteria. The initial amount of bacteria is just this coefficient 100. This one does not depend on any computation. Okay, it's just 100. And sometimes, if this expression is not such standard, you have to let t be 0. If the expression is not in this form, you need to let t be 0. So for example, I just say for example, maybe your expression looks like this. If your expression looks like this, you have to let t be 0. Okay? The initial amount is a number when t is equal to 0. If this happens, it becomes 100 at t equal to 0. It's 100 e to 0.045 times 0 times minus 10 is negative 10. It becomes 100 e to negative 0.45. Okay, so this one is simple. Whenever you have the standard form, the n0 e to kt, because when t is 0, the second part is 1. It disappears. You only have n0. So the n0 is the initial amount of bacteria. So you don't have to do anything. But, I just say but, if you case like this, you have to really let t be 0. This is a standard, not standard. This is the universal way to find it. Okay, t is equal to 0. It will give you the initial amount. Second, the growth rate. What is the growth rate of the bacteria? The growth rate of the bacteria is a coefficient of t, 0.045. It's a 4.5%. Well, either way, you can just write this, or you write this. It doesn't matter. You don't have to change it to the percentage. Okay? You don't have to do that. What is the population after 5 days? The population after 5 days, you just let t be 5. Okay, so 5. So that is n of 5. You multiply 0.045 by 5, you get what it is, 0.225. In the exam, once again, in the exam, this is the final answer. You can never approximate it. Okay, Now we can, with a calculator you can do it, but we cannot use calculator. So this is a answer. It's approximately 125.2 grams. Okay, this number is necessary in the exam. It is necessary, and you can never write this number in the exam. You stop at this step. Okay. How long will it take for the population to reach 140 grams? Well, you know the weight of population, so it's 140. The initial, where is the initial? Here, 100 times e to 0.045 t. So you're looking for the time t. Now let's look for the time t. We divide the two sides by 100, we get a 1.4. And once you reach this step, you're looking for the exponent, natural logarithmic function. Okay, so you apply natural logarithmic function, you will get a natural log of 1.4 is equal to 0.045 times t, and you divide it by 0.045, you get t is equal to this. Again, in the exam, this is a final answer. This is a standard answer. Don't do any other simplification or estimation. This is the answer. And in the textbook, they provide it's about 7.5 days. Okay? E. What is the doubling time? For the population. What is the doubling time for the population? The initial population is 100. Double it, you have 200. You actually do the same process. You just change the number from 140 to 200. You divide the two sides by 100, you got a 2. And you do the same process. You get a natural log of 2 is equal to 0.045 times t. So t is a natural log of 2 over 0.045. Again, this is a final answer. Don't ever estimate it. Okay? Don't ever estimate during the exam. I'm talking about the policy in the exam. You cannot use calculator. Okay, so that's the standard questions about this the law of exponential growth. Okay. And this problem is standard because you have the complete formula. You have a complete formula. You can just plug in t, or you solve for t. Sometimes you don't know the initial value. Sometimes you don't know this growth rate. So you have to use some properties to find the initial value or the growth rate. Okay? Let's see another one. Example, a colony of bacteria. Colony of bacteria increases according to the law of uninhibited growth. Okay, A, if n is the number of cells and T is the time in hour, express n as a function of t. Okay, so you can measure the bacteria in grams, or you can measure the bacteria in numbers. So it doesn't matter. So the n of t is always n sub 0 e to kt. So whenever it says according to the law of uninhibited growth, it's always like this. Okay? B, if the number of bacteria is doubles, not is, doubles in 3 days. Doubles in hours. Hours, not days. In 3 hours, find the function that find the function that gives the number of cells in the culture. Okay, so we know that the number of the bacteria doubles in 3 hours. So let's check it. This n sub 0 is the initial value, initial amount of bacteria. After 3 days, so after 3 hours, it becomes 2 times n sub 0. Okay, so after 3 hours, the number of bacteria doubles. So when t is 3 hours, the number of bacteria is 2 times n sub 0. So this is our condition. And we're looking for this coefficient k, the growth rate. Okay, so you see here the real number of bacteria at the beginning does not matter because they are cancelled. Okay, and then you take the natural log of 2 sides. Log 2 is 3k, and so k is log 2 over log 2 over 3. Okay, so the coefficient is the function is like this: nt is equal to n sub 0 e to log 2 over 3 times t. This is a function. This is the function. Don't simplify it. Don't estimate it. You cannot do that. Okay. Okay. So by this condition, doubles in 3 hours, we can determine the coefficient. We can determine the growth rate D, C, C or D, C. How long will it take for the size of the colony to triple? The size of a colony triples, so the initial number is n0 triple. The current number is 3n0. Of course, we still use the same growth rate here, and we're looking for the time. And once again, you can see that in this equation, this n sub 0 is not important because it will be cancelled. It will be cancelled. Okay, so we're looking for this t in this moment. We take the natural log of two sides. So t is equal to natural log of 3 over natural log of 2 over 3. It's a natural log of 3 times 3 over natural log of 2. It's a 3 times natural log of 3 over log 2. So after such hours, the size of a colony will triple. Okay? D. How long will it take for the population to double a second time? Okay, so a second time, that is increase 4 times. Okay, so in 3 hours, the population grows from n0 to 2n0, and actually in another 3 hours, one n0 grows to 2n0, another n0 also grows to 2n0, so it's a 4n0, it's a 4 times, right? So this is exactly the 6 hours. Every 3 hours, the size of the colony will double. Every 3 hours. So this does, remember that we discussed the time for the population double does not depend on the initial value. Here you double the population with the initial value n0. Here you double the population with the initial value 2n0. For any size of initial value, the time to double the population is fixed. Okay, so after 6 hours, the population will double second time. Second time 3 hours, first time 3 hours, so the total 6 hours. First 3 hours, the size doubles. the second 3 hours, the size doubles again. In total, 6 hours, the size increases 4 times. Okay, that's the correct answer. Okay, that's the correct answer. Okay, so this is the application of exponential functions. So we have to tell the story, and the story is not the main part of the mathematics. So sometimes I need time to read the problem. We need time to understand the story. Okay, let's see another thing. It's a radioactive decay. Radioactive, it's a word from the physics, or sometimes you can read it from the chemistry. Therefore, the kernel stuff, which I don't understand a lot, but let's just talk about mathematics. So the uninhibited radioactive decay. Okay, that is a uninhibited growth rate, right? This is a uninhibited radioactive decay. So the amount A of a radioactive material present at time t is given by A of t is equal to A sub 0 e to kt. But here this is decay, so k is less than 0. K is less than 0. It's a negative number. Like the previous problem. In the previous problem, we learned that the time so that the size doubles is fixed. The time for the size doubles is fixed, and that's double because k is a positive. If k is negative, we talk about half-life. So all radioactive substance, all radioactive substances have a specific half-life. Half-life means the time so that the size becomes half of the initial size. Okay, half of the initial size. This is called the corresponding time is called the half-life, which is the time required for half of the radioactive substance to decay. Okay, half of the radioactive substance to decay, that's called the required time is called the half-life. And in the there's a technique called the carbon dating. The carbon dating, it has certain proper half-life so that we can use it to detect the time of certain material. Okay, so let's see the example. The carbon dating is some practical tools to determine the age of some ancient stuff. That technique uses a half-life. Okay, let's check the problem and we understand this. So traces of burnt wood along with ancient stone tools in an archaeological dig in Chile were found to contain approximately 1.67% of the original amount of carbon 14. So this is some radioactive material, radioactive substance, carbon 14. It will be used in the carbon dating. That's why it is called carbon dating. If the half-life of carbon 14 is 5,600 years approximately. One was the tree cut and burnt. Okay? So basically the theory is the following. When the tree grows, the carbon 14 in the tree keep certain level. When the tree is cut and burnt, the amount of the carbon 14 start to decay. And that process satisfy this uninhibited radioactive decay formula. And after several years, many years, the carbon 14 in this burned wood is just 1.67% of the original carbon 14. For example, originally for this amount of wood, we know it should contain certain amount of carbon 14, but after test, this burned wood only contain the 1.67% of the theoretical carbon-14. So that's the story here. And we also know that the carbon-14 has half-life 5,600 years, which means every 5,600 carbon-14 we will lose half of the carbon-14. Okay? Okay, so now we need to understand how do we use this 5,600. Okay, so after 5,600 years, the initial amount becomes half of it. So you see here, this is T. T is a 5600. K is that coefficient. It does not change. It only depends on this carbon-14. And the initial amount of carbon-14 becomes half of it. We really don't care the precise value of the initial amount because N0 will be cancelled. And then we take natural log of two sides. And then we divide this equation by 5600. We get the K is natural log of 1/2 5600. And this is a negative number. Why it is a negative number? Because it's 1/2 is less than 1. Sorry. 1/2 is less than 1. It's a negative number. It's like this. When this input is greater than 1, it's positive. When the input is less than 1, between 0, it's negative. So that's why it's a negative number. It fits our theory. Okay, so it's a natural log of 1/2 over 5600. This is the constant K, and this is why we find the constant and we find the relation between constant and half-life. After we get this K, what we are going to do? We are going to estimate the time. Here is the time. Time is known. Time is known, we get K. And once K is known, we can find the time. How do we do that? You see, current moment, we only have 1.67% of the original theoretical amount. And initial amount, exponential natural log 1/2 over 5600. This is K and times T. Okay, we're looking for the proper time T that corresponds to this percentage, 1.67%. Right? Okay, same process. We cancel this initial value. You get, this is 0.0167. And this is E natural log 1/2 5600 times T. In our problem, we have this number. We're looking for the corresponding time. And we take the natural log for two sides. Again, we get the natural log 0.0167 is equal to this natural log 1/2 5600 times T. So we move this 5600 to the left side. It's 5600 times the natural log 1/2 and times T. And we divide it by the natural log 1/2 natural log. So we get T is equal to 5600 natural log 0.0167 over natural log 1/2 is 0.5. I don't want to copy this 1/2 a lot. Okay, so this is the form of the answer in the exam if you see some similar problem. Okay, this is the answer. Don't ever simplify it. you don't know how to simplify it without a calculator. I don't know either. Okay, so that's the answer. That is the answer. Always keep them. Don't use calculator. It's not allowed. And of course, in practice, you can use a calculator. This number is approximately 33,003 years. I mean, you can ignore the 33,000. So this wood was cut and burned 33,000 years ago. So that's a way to use this carbon-14 to date the ancient material, especially with wood, because with the wood it contains a carbon-14. To have a stone, there's no carbon-14, right? Okay, so that's the first two topic in this section. Then section has several scattered material, but all these material are related to that exponential function. So the first two, we get exponential growth and exponential decay. Growth normally measure the amount of the bacteria in certain culture. Decay normally describe the radioactive substance. So you study those two properties, those two problems again, and try to understand the computation. But in principle, we have this exponential function. Sometimes, if you just double or triple the amount of the material, this a sub 0 is not very important. It can always be cancelled through the process. So basically, you have to study k and t. You know k, you can find the t. You know t, you can find the k. Right? So it's just a back and forth process. Okay, so we finish this video, and we will start another video to talk about the other part of this section. Do your exercise, send me email if you have questions. Okay, we'll stop this video.